In this tutorial, I'll be manually accomplishing a PCA of some sample data. Now normally you wouldn't be doing this manually. You would be using one of the many R functions available for principal components analysis. However, my goal in doing this is to expose you to the terminology and concepts in PCA such that when you do use one of those built-in functions, you'll have a head start. You'll understand the terminology and you'll be in a better position to defend your analysis of the data. So I'm going to go ahead and get started here. As is mentioned in the description, this code that I'm using can be downloaded, so refer to that for the relevant links. I'll probably be cutting and pasting in here since I'm not such a great typist and I don't want to slow us down. So let's go ahead and read in some data. As you can see, I'm reading in something called My Classes, and what this is a data set that represents 100 students, all of whom took tests in physics and statistics. And what this data set contains is the respective score in physics and statistics. Now, one of the first things that is natural to do is plot the data, and you can see I've already done that. We can do it again here. And one of the first things that jumps out is that there is a high degree of correlation between the physics and statistics scores, so this would probably be a good candidate for linear regression. On the other hand, when we look at the information, we may want to attempt to discriminate between which subject has the most variation. In other words, are students doing better at statistics or physics, or more or less the same? And here we can see that if you're good at physics, this student pool, you tend to do better at statistics, or you tend to do as well at statistics. But it's not apparent which topic or which subject has the widest variation. Now obviously the data is very simple. We could drop down to the command line here and do some descriptive statistics and come up with our own conclusions. On the other hand, let's apply some principal components concepts here to see what we can come up with. Now, let's commence with the principal components analysis. One of the first things that we'll need to do is standardize the data. To accomplish that, I'm going to define a function called standardize. And as you can see, it takes a data point and subtracts it from the mean of all the other data. So we're going to apply this to our data set that has physics and statistics scores. And I create a variable called my.scale.classes. Let's plot that, and you'll see that it's the same data. The relationships are preserved, although the limits, the domain, now reflects the scaled nature of the data. So we haven't changed the data. All we've done is change the scale of the data. Now, as I mentioned previously, or was mentioned in the initial splash screens, PCA is a technique that allows us to accomplish dimensionality reduction and uncover latent patterns in the data. To do this, it borrows heavily from concepts in linear algebra, such as eigenvalues, eigenvectors, and singular value decomposition. Now, I don't want you to get intimidated or scared off by these ideas, but because we're using them, we have to borrow some of that terminology. So I want you to get comfortable with that, because this is at the heart of the PCA. Now, our data has the same units of measure in both cases. In other words, it is presumed that this data is on the scale of 0 to 100, the typical exam score scale. As we can see, some of our students didn't do so well, but that's okay. The measurements are still in like units. Now, because of this, we can standardize the data simply by mean centering, and then we'll use the covariance matrix. However, if our data had mixed units, for example, salary, weight in pounds, height in inches, then we would have had to mean center and divide by the standard deviation to get unit variance, and then use a correlation matrix. All right. The reason I'm pointing this out now is because when you use the built-in R procedures, you're going to have to make a decision about which approach to use. So while it seems like an unnecessary complication, at this point it's actually information that will pay off later when you use the real procedures. Okay, since we're going to use the covariance matrix, let's call the necessary R function to generate that. It's quite simple. You see we have the covariance matrix there. And we're going to call the eigenfunction, which will give us the eigenvalues and eigenvectors of this matrix. Alright, let's run a couple of more commands here to make things a little bit more understandable. Okay, so if we take a peek at the results of the eigenfunction, what we're going to see here are a couple of things. We'll see the eigenvalues in this row, 155.28 and 3.97. And one of the first things that you can notice is that the sum of the eigenvalues in fact represents the total variance in the data set. So it's this magic that allows us to exploit the eigenvectors, which are also known as the principal components. The vectors are right here. The way to view this is that the columns here are the eigenvectors. So minus 0.719, minus 0.69, that's the first eigenvector. The second one is over here. Now I've renamed these to make them more comprehensible within the context of principal components analysis. So what we're seeing here is that PC1, aka eigenvector 1, is a linear combination of these two variables, physics and stats. And these coefficients, you can consider them as such, can also be called loadings. That's a concept in PCA that you'll hear quite frequently. Now what this information does here is indicates the strength of the association of these variables with the principal component. You can see in this case that they trend together. Over here they trend apart. Now we'll talk a little bit more about this when we discuss the notion of biplot. But I wanted to point out that by finding the eigenvectors of the covariance matrix, we have in fact found the principal components. The other important concept here is that the loadings, I'll go ahead and create a variable with that information. The loadings in PCA is the term for this information, these coefficients. Now one thing we might do is take the eigenvectors that we found, compute the slope of that vector, and plot it, overlay it on the existing data so that we can see the relationship between the data, the scaled data, and the eigenvector. So I'd like to go ahead and do that for you. So first we'll compute the slopes. Next we'll call the AB line function and text xy to see what's going on. Now this is pretty interesting. The red line is the first principal component, the first eigenvector. The second line is the second eigenvector, also known as PCA2. Now one thing that you'll notice, let me stretch this out for you to make it more apparent, is that these two vectors are orthogonal, they're perpendicular. That's by design. It's a property of the eigenvectors and the principal components. Now what do we see? The first thing that we see is that PC1 appears very much to capture the larger part of variation in the data set. You can see here that this line cuts through or outlines most of the variation. PC2, however, carves out the remaining variation, and it isn't very much, but that's the way PCA works, is you hope to find most of the variation within the first few components. Now since we have two variables, we have these two components. The first one seems to find most of it, the second finds the remaining. Now, a legitimate question is to determine exactly how much variation each component accounts for. So what I'll do is take the eigenvalues, divide it by the sum of the eigenvalues, which is the total variance in the data set, and multiply that by 100. And that will give us the percent variation that we're looking for. So if we look, we see that PC1 accounts for 98%, approximately 98% of the variation. PC2 accounts for roughly 2%. So this gives us an estimate, a pretty accurate estimate of how much variation each component accounts for.